When you're falling in a forest and there's nobody around, do you ever really crash or even make a sound? When you're falling in a forest and there's nobody around, do you ever really crash or even make a sound?
Well, to answer that question, yes, you do make a sound, and you make a sound, and we know that because of compressional waves. Compressional waves are another type of mechanical wave, and this is how sound travels. So let's look at them a little more closely. Compressional waves, also known as longitudinal waves, are a mechanical wave in which matter in the medium moves forward or backward along that same direction that the wave travels. So this time, instead of thinking them as going up and down or side to side, they are simply going out. Think of your voice when you speak, it simply goes out away from your body. If you have a slinky, it would be a good time to take it out and look at it. This is what a compressional wave looks like if we were able to trap it into midair. It's that grouping of coils that squish together and spread apart and squish together and spread apart. That's exactly what a compressional wave is. So again, in your learning log, please take a little diagram. In this diagram, so simple. A few of your lines are going to be spaced out while others are going to be clumped together. Then spaced out, clumped together, spaced out, clumped together. Very technical terms here, I know. If we're looking at our diagram now, our first section is going to be the compressions. And this is the piece of the compressional wave where those particles are crowded together or squeezed together. So if you think of your voice as being that slinky, when those bands are squishing together, that's called the compression. Makes sense, right? They're compressed, they're squeezed together. The next part is a little bit harder to say, but it's just simply where those lines, that sound is spaced out, and that's called the rarefaction. Say that word with me, rarefaction. It's the part of the compressional wave where the particles are spread apart. So again, going back and forth, they're going to be compressed, and then there's a rarefaction. Compressed, and then there's a rarefaction. Now, just like with that transverse wave, we are going to measure compressional waves with a wavelength. The wavelengths are going to be the distance from compression to compression or rarefaction to rarefaction. It's no different than the transverse wave, guys. The only difference is our parts have changed a little bit. So pick one point on your wave. If you're going to pick a compression, go for it. And then count how many bounces is it to the next compression. Here's one. How many bounces to the next compression? Here's two. And if we were to keep looking at this, again, just like I said before, I find it easier if we look at what's on the outside. So because there's rarefactions on this wave on the outside, let's count from here. 1 rarefaction to the next, 2 rarefaction to the next, and 3 rarefaction to the next. That gives us 3 wavelengths in this segment. Finally, I just wanted you to be able to see a little bit of what that sound would look like if we isolated it from a drum. So here's all those air molecules that are just sitting there in the air. And if we were to bang on that drum, that sound wave would take those air molecules and squish them together. Remember, this is called the compression. As that travels out, the compression is going to move and the rarefaction is going to stay behind. This is going to continue to bounce back and forth as it travels to hit your eardrum where you are going to be able to hear it. So remember, compressional waves, they are just like a transverse wave. However, they're going to carry a different thing, and that is sound.